r of t equal to 6 cosine of 5t, comma, 4 sine of 5t. And the question is, what kind of curve does this describe? Well, it's kind of circle-ish, right? It's almost a circle. If the 6 and the 4 weren't different, like if those were the same coefficients, we would certainly have a circle. Just to kind of, in fact, let's kind of examine that just for a moment. If we had r of t, say, equal to 4 cosine of 5t, comma, 4 sine of 5t. If we're thinking of this as our x and this is our y, then it's certainly true here that x squared plus y squared is just equal to 4 cosine of 5t squared plus 4 sine of 5t squared, which is really just 16 times cosine squared plus sine squared, which is really just 16. Meaning this position function here is really just telling you the graph of a circle, right? We have x squared plus y squared equal to 16. So if the cosine and the sine happen to have the same argument and the same coefficient, we're usually plotting out a circle. But if you've got different coefficients, you've got something not quite circling. It's an ellipse. And the way we can kind of see that is by doing the following. So usually if you're trying to make something that you know is an ellipse look like an ellipse, I'm still going to think of this as x. I'm still going to think of this as y. And then my usual way of going about it is divide each thing by the thing that's the coefficient so that we can get rid of it. So I'm going to say that x over 6 is equal to cosine of 5t, and y over 4, that's going to be sine of 5t. And then I know that cosine squared plus sine squared is equal to 1. So that's going to be the equation. X over 6 squared plus y over 4 squared is equal to 1. And that is definitely the equation of an ellipse. And you could write it like this. It's more standard to write it as x squared over 36 plus y squared over 16 equal to 1. There are probably other ways of going about this, but that's the way that it looks easiest to me. I suppose we could also graph it to kind of see what's going on. So if we graph this ellipse, got a major axis on the x-axis of 6, or I guess I should say 6 from the origin. X of y is 0, x to be plus or minus 6, and a minor axis length of 4 from the origin. Here's our ellipse. It looks kind of like this. Ellipses have never been my strong suit for drawing. May I ask James Boyle? And then I guess we can talk about the direction it's going. So if we start at t equal to 0, well, r of 0 is going to be 6 times cosine of 0, 4 times sine of 0. So here we're starting at t equal to 0. And then if we plug in, I would probably go with pi over 2 next. At t equal to pi over 2, we're going to get r of pi over 2. Pi over 2 is probably a bad choice. Not a bad choice. It's just not the most thoughtful choice I could have made. Because when I plug in pi over 2, I'm really going to get cosine of 5 pi over 2 and sine of 5 pi over 2, which means I might have kind of already done a full revolution. So I'm not really sure which direction I'd be going. So I might need to go a little bit less, although I can certainly find what this is. 5 pi over 2 is pointing upward. So that's going to be 6 times cosine of 5 pi over 2 is going to be 0. And sine of 5 pi over 2 is going to be 1. So 4 times 1 is 4. But if I go back a little bit, well, I don't know. I'm trying to think about this the right way. No, that's totally fine. I would probably think about having a smaller angle, like if t was equal to, I don't know, say pi over 2 divided by 5. Then if I plug that in, I get r of pi over 10, and that's going to be 6 cosine of pi over 2, 4 sine of pi over 2. It's still giving you the same position. It's just this one we got here is kind of, you've already gone all the way around once. So it's hard to know what direction the particle is traveling in, if that's a question we're interested in answering. But here, if we plug in pi over 10, we get just 6, 0 as well. Sorry, 0, 4, apologies. So yes, here's t equal to pi over 10. And then I imagine this would be t equal to pi over 5, and t equal to 3 pi over 10, so on and so on and so on, around and around and around. All right, let's look at one more example in 2 dimensions, then we'll kind of move into a 3-dimensional realm here. So let's look at this. Let's say we want to figure out what kind of graph this vector valued function is describing. Got the cube root of t plus 1 for the x coordinate, and 2t minus 5 for the y coordinate. Oops, sorry, I can't see that. Apologies. So typically, if we're trying to see what does the graph of this position vector or this vector position function look like? Well, if you have no reason to kind of go one way or the other, I would start by trying to solve for the x coordinate, meaning I'm thinking of this is x, this is y, and I'm going to solve for, actually, I said the wrong kind of, I'm going to solve for t in terms of x. So I'm going to take x equal to the cube root of t plus 1 and solve for t. If I do that, I get x cubed equal to t plus 1, x cubed minus 1 equal to t. And then we're going to substitute that in for the y equation. So y equals 2t minus 5. If I then plug in x cubed minus 1, I get y equal to 2 times x cubed minus 1 minus 5, which is equal to 2x cubed minus 2 minus 5 is minus 7. So now we have a decent idea of what this graph actually looks like. Actually graphing this without doing this would be challenging. But here, we have a pretty decent idea. Well, I know what a cubic function looks like. I'm just subtracting 7. So I would plot maybe x equal to 0, y equal to -7, and x equal to 1, and y equal to -5. Maybe x equal to -1 and y equal to -9. To get an idea that this kind of looks like this. There's an idea of what our graph looks like. And we could even label a couple points like right there, when t equal, well, actually right there, I should say, that point there at 1, -5 is when t is equal to 0. And if we plug in t equal to -1, we get x equal to 0 and y equal to -7. So we can see that we're going, and I've maybe drawn my arrows in a misleading way, which is always kind of the problem with these vector value functions. You want to draw the graph kind of like you're used to drawing the graph with arrows at the ends. But if I'm trying to indicate the direction the time is flowing forward, my arrow should really be going this way. Let's do one more interesting, because there's one more thing I just kind of thought of that I think is pretty interesting when you talk about these vector value functions. So let's say we had something, we'll make one very kind of basic, and then we'll make it a little bit harder. So let's say we had some vector value function like this, r of t equal to t comma t squared minus 2. And this one is about as easy as it gets to do the graph, because we can just say, great, x equals t, and then y equal to t squared minus 2 becomes y equal to x squared minus 2. And I can definitely graph that parabola. And at the point 0, -2, there's where t is equal to 0. Point 1, -1, there's where t is equal to 1, and so on and so on. And of course, I did the thing again that I just said I shouldn't do. I do the arrows like I would normally draw a parabola. That's just life. It's hard to break those habits. But really, we should be going this way because that is the direction where time is increasing. Okay, here's where things I think get a little interesting. What if we had R of t equal to e to the t, e to the 2t minus 2? If we're not super careful here, we might end up thinking that we get the exact same graph. I'm going to say that x is e to the t and y is e to the t squared, which is e to the 2t minus 2. So y does equal x squared minus 2. But the difference here between the graph I'm about to draw and the graph I just drew is that here we have a limited domain, right? If x equals e to the t, then for sure x has to be greater than 0 because e to the t is always greater than 0. In a similar way, since y is equal to x squared minus 2, bless you, y is going to have to be greater than 0 minus 2. So essentially, we're getting this graph, except we're almost starting at the point 0, -2. So we're not quite getting that point. So what we're really getting here, an open point there. I guess I'll plot a couple points here. X is 2, y is going to be 2. So we have something that looks like this, essentially just the right half of this parabola. And you get weirder points, right? Because, like, for example, if I plug in t equal to 1, I get x equal to e and y equal to e squared minus 2, which is somewhere like over, I don't know, like up there. There's t equal to 1. I guess t equal to 0 would have been easier to plug in. Plug in t equal to 0, I get x equal to 1 and y equal to -1. And then if you plug in a bunch of negative, it's kind of interesting. This little section right here, between that point and that point, is where t goes from -infinity to 0. Kind of interesting. Anyway, that's just kind of to point out that even though you might get the same relationship between x and y, you might get a different graph for the relationship based on what x and y are allowed to be. Because here x is positive. You could do the same thing. I'm not going to graph this one, but you should check out on your own what happens if you were to graph something like, I really don't want to draw it up there. Do it right there. You should try on your own plotting the function r of t equal to, say, like cosine of t, comma, cosine squared of t minus 2. Excellent question. So since x is e to the t, well, what's the graph of e to the t look like? Looks like that. And it's never negative. In fact, it's never even equal. It's never not positive. It's always positive. So since e to the t is always positive, if I'm graphing y versus x, x has to be positive because x is equal to e to the t. So even if t is really, really negative, like -1,000, e to the -1,000 power is still positive. It's a very, very small positive number, but it's definitely still positive. That's kind of what's happening there, is that we are limited into what x can equal because of how x and y are defined parametrically.
If there wasn't like -2, so you can graphically move up, right? So we could go like towards the left side, right?
Totally. Like we could, if we wanted to, for example, we could change it so we had something like r of t equal to e to the t minus 3 and e to the, let's make it e to the 2t again, plus 1. So now x equals e to the t minus 3. I'm going to still solve for e to the t to make it a little bit easier. So x plus 3 equals e to the t. I don't find any value in this particular example in solving for t. Like I don't need to write down that t is equal to the natural log of x plus 3. Because I can say right over here, y is equal to e to the 2t plus 1, or more usefully, y equals e to the t squared plus 1. Then I can substitute that in there and get y equal to x plus 3 squared plus 1. And although you could multiply this out, you actually really don't need to, because I know how to graph y equals x plus 3 squared plus 1. That's the nice vertex form of a parabola. So I can see that this is going to have a vertex of -3, 1. Great. Well, just like before, e to the t is still always positive. So x equaling e to the t minus 3 has to be bigger than 0 minus 3, which is -3. So we're essentially starting at the vertex. We're saying, great, the vertex would have been -3, +1. I should say we're almost starting with the vertex. We don't actually get that point. So we're going to almost start right there, and then we're just going to go up and up to the right. So we're going to get, yeah, sorry, I just want to see what my 0, 10. Okay. So it's going to look like that. Yeah. So you can certainly move things left or right, but because x is equal to something with a limited range, you only get certain values for x. You can't get the left side of this. On the other hand, just to go back to this other example here, if you graph this one, it's very limited. You can only go so far to the right and so far to the left because of how not many values you get when x is equal to cosine and y is equal to sine. Sorry, when y is equal to cosine. Right. And yeah, and you're right. And it goes back. Okay, fine. I can, like I've talked about it enough. If we do that one. Well, again, we're still getting y equals x squared minus 2. Right. It's not a surprise. We know that x is cosine. We know that y is x squared minus 2. But now x is limited. X is between -1 and 1 because x equals cosine of t. Y is also limited. Y is actually can only be between -1 and -2. Right. The smallest cosine squared can be is 0. The biggest cosine squared can be is 1. So y is going to end up being between, I mean, you don't really need to actually say that because we're going to get it from the graph anyway, but y is going to be between -2 and -1. So here we get the portion of the graph, well, if x is 1, y is going to be 1 minus 2, which is -1. If x is 0, y is going to be -2. If x is -1, y is going to be -1. So we just get this portion of the parabola. And sorry, it's drawn poorly there. But then it kind of goes, like Patrick was saying, back and forth, right? If we start at time equals 0, well, time equals 0, cosine of 0 is 1, and y is going to be 1 minus 2, which is -1. So we're going to start here at time equals 0. And then if we go to, like, say, pi over 2, here's time equals pi over 2, and then here's time equals pi. Then if you keep going, we're also here at time equals 3 pi over 2. And we're back here at time equals 2 pi. So we just kind of keep going back and forth. You go this way, then you stop and you go back the other way, and you keep going back and forth. Interesting. So just because you get the relationship of y equals x squared minus 2 does not necessarily mean you get the entire graph representing that. It really depends on what x and y are defined to be equal to. It's kind of neat. Let's look at some different examples. Let's say we want to graph. We'll see how this goes. We want to graph the position function r of t equal to cosine of t, sine of t, t squared. And what I would observe here is that the x and y coordinates, right? X is cosine, y is sine. That's just going to send us in a circle. We know that x and y part of the curve is traveling around a circle. A radius 1. And then what's going to happen is t increases, we're going to go around this circle, but then the height is going to get larger because the z part of this position function is equal to t squared. So z is going to increase as t increases. So if I were drawing this, yeah, which I am. Yeah, let's go that way. X, Y, Z. So that's 1. Sure. So here's my circle of radius 1. And so at time equals 0, r of 0 is just going to be cosine of 0, which is 1, sine of 0, which is 0, and 0 squared, which is 0. So we're starting right there at time equals 0. Then let's say pi over 2. Well, now cosine of pi over 2 is going to be 0, sine of pi over 2 is going to be 1, and pi over 2 squared is going to be how high we are. I would say pi over 2 is about 1.5. 1.5 squared is about 2 1/4. So we're definitely moving quite a bit up. Maybe about right there. So we're kind of going up like this. Let's use a different color, James. And then at say pi, we're going to have, well, cosine of pi is -1, sine of pi is 0, and pi squared is like 9, bigger than 9, actually, what you know. Right, so we're up here somewhere like this. And so we're just kind of doing this thing where we're circling around sorry, and I've kind of run out of room there, but we're circling around this kind of cylinder. And we're just getting higher and higher and higher, still kind of just traveling around the outside of the cylinder, going up and up and up. It's called a helix. Kind of like DNA fame, right? The helix, that's what I'm going for there. And we could also talk about, just for a moment, the velocity at any of these points. So velocity, still just the derivative of position. That's going to be, let's see, derivative cosine is negative sine. Derivative sine is cosine. And derivative t squared is 2t. So for example, if I want to find the velocity at time equals 0, that's going to be the vector 0, 1, 0. So at time equals 0, my velocity vector is pointing wholly in the y direction, just like that. And at time equals, say, pi over 2, the velocity at pi over 2 is going to equal, well, again, negative sine of pi over 2 is going to be -1. Cosine of pi over 2 is 0. And 2 times pi over 2 is pi. So now my velocity vector is pointing both, well, it's pointing in the negative x direction, so back away from us. And then it's pointing upwards as well. So it's pointing back and up. Kind of like that. And even though my picture might not do a great job of displaying it, it is tangential to the direction of travel, right? We are going up like this, and right there, if we just kept going, we would keep going straight back and up. Okay, let's do something interesting. I mean, I think it's all interesting, but let's continue with this interesting question. Let's ask ourselves, what's the angle between the velocity vector and the acceleration vector, which we haven't found yet, at time equal to pi over 2. Okay, well, we already found the velocity vector at pi over 2. We can write it again. V of pi over 2 is -1, 0, pi. And to find acceleration, we're going to take the derivative of velocity. So acceleration at t. So here's our velocity vector, negative sine cosine 2t. So acceleration vector is going to be negative cosine of t, negative sine of t, positive 2. And if we plug in pi over 2, acceleration vector at pi over 2 is going to be, let's see here, negative cosine of pi over 2 is 0, negative sine of pi over 2 is -1, and 2 is just 2. It's kind of interesting. I also like to kind of think about the direction the acceleration vector is actually pointing. So we go back to our picture for just a second. At this point here, if we're going 0 in the x direction, -1 in the y direction, so left, positive 2 in the z direction, we're kind of going left and up. It's kind of hard to see what's happening, right? I mean, I think it's hard for anyone personally to see what's happening. Some people are definitely better at visualizing than others, but don't beat yourself up about it if you feel like you're having a hard time seeing exactly what's happening. You don't have to necessarily be able to see it. I'm just trying to help you maybe see it a little bit. So let's see. If I were trying to figure out what the angle between these two vectors were, I would really quickly just ask myself, are they perpendicular? They're probably not, but I don't want to do all the work and then find out they were perpendicular. So if I take their dot product really quickly, I get 0 plus 0 plus 2 pi. Okay, not perpendicular, but worth checking because maybe they would have been and it would have been easy to find the answer. So the angle is going to be, I know the cosine of the angle is going to be the dot product of the vectors, a of pi over 2 dotted with v of pi over 2 divided by their magnitudes. It's messy to write. Okay, so let's see. So we just said that a dot v was going to be 0 plus 0 plus 2 pi. And the magnitude of a is the square root of 0 squared plus 1 squared plus 2 squared, square root of 5. And the magnitude of v is the square root of -1 squared plus 0 squared plus pi squared. So 1 plus pi squared. And then we would end up getting theta equal to the inverse cosine of 2 pi divided by the square root of 5 times the square root of 1 plus pi squared. Did I actually bring my calculator? I meant. And we could find what that angle was, but really, if I was actually answering a question in the exam, I'd leave it like this. Ooh, always a fun. So just a quick check. This angle is definitely acute. Theta is acute because we're taking the inverse cosine of something positive. Because the argument of the inverse cosine function is positive. Right. Okay. Oh yeah, let's do. I want to do the fun example, not the not fun example. But I feel like I need to, so yeah. So we'll come back to that maybe. Let's go on to this other because I think it's worthwhile. So yes. Let's say we want to solve an initial value problem. So we are given that the second derivative position, d squared r dt squared, if you like, or if you prefer, a of t, right? The second position of the second derivative of position is typically thought of as acceleration. So we're given that the acceleration of this particle is equal to -6, -6, -6. Right, like this, or you can write it as -6i minus 6j minus 6k. Either way you want to write it. We're also given some initial conditions. We're given that the initial position at time 0 is 1, 2, 3. And we are also given that the initial velocity at time 0, which you can either write as dr dt at t equal to 0, or just v of 0, is equal to 4, -5, 0. Based on that information, we want to find r of t. Excuse me. Well, like most problems, when you're given acceleration and asked to find position, we're going to end up doing a couple of anti-derivatives essentially. So we're going to start by taking your acceleration vector and anti-differentiating it to get the velocity vector. So the velocity vector here at any time t is going to be the antiderivative of this vector, -6, -6, -6 dt. So integrating a constant is pretty straightforward. We're just going to get -6t, but we have to add. So just like when you normally integrate, if it's an indefinite integral, we have to add on a constant. So we're going to get -6t plus a constant called c1, and then -6t plus another constant, but we don't know that those constants are the same. So we're going to call it c2, and then -6t plus c3. And if we're lucky, we are lucky here, we're already given the initial position from the initial velocity at time equals 0. So we can say, well, great, this is equal to v of t, but I also know that v of 0, which if I plug in 0 here, I get 0 plus c1, 0 plus c2, 0 plus c3. That's just going to be c1, c2, c3, but that's equal to the given initial condition for -5, 0. So now we know that our velocity vector is just -6t plus 4, -6t minus 5, and -6t plus 0. And then we can kind of do the same thing to find the position. So I'm going to integrate again. And now when I do that, I get, let's see here, -6t squared over 2 is going to be -3t squared plus 4t plus another constant. Let's call it k1 instead of c1. And then same deal here, -3t squared minus 5t plus k2 and -3t squared plus k3. But we're given r of 0. So r of 0, all the t's are going to go away, and you're just going to get k1, k2, k3. And we know that r of 0 is equal to 1, 2, 3. So we're going to end up saying that our final position vector is going to be -3t squared plus 4t plus 1, comma, -3t squared minus 5t plus 2, comma, -3t squared plus 3. And that gives us the position vector that has the acceleration being -6, -6, -6, and meets these initial conditions. Not too terrible. It just feels like it's a little messy. There are harder ways of asking this question where you don't get given quite as much information, which we'll try to explore, but maybe not today. Let's see.
Why did we add it again?
So whenever we integrate, just in general, right, like back in 21B, if you're finding an indefinite integral, you typically add a constant on.
Oh, we integrated it.
Right. Well, yeah, exactly. Right. To get from accelerate. So v of t, right? This is the integral of your acceleration here. In a similar way, when you're finding r of t, this is the integral of your velocity. So that's why, yeah. Yeah, we got time. Okay. Let's go back and look at, yeah. Look at this example here. So there's a pretty well-known vector valued function that you may have seen in class, you may not have. Called the cycloid. And as Grant has said it to me a few times, the way he likes to think of it is it's the path of a bug that has been squashed on a tire. All right, the bug gets smushed and then it just kind of goes do. But like it looks so like it kind of looks like it's going in a circular pattern, but it's not actually, because right, we're thinking about, at least I'm thinking about the wheel kind of starting with the bug getting smashed right there. The bug got smashed at the bottom of the wheel. Let's draw this wheel. And then it rolls forward. And so maybe a little while later, say, yeah, I want to draw this so it doesn't look terrible here. Right, this position has rolled up to say like right there. And what we typically do is we kind of think about how that position looks compared to the angle we've rotated through. So there's the angle we've rotated through. And I'm going to try and make that bigger to kind of help us see what's happening here. So like here, we would say the angle is 0. And here we've got some angle. It looks, I don't know exactly what it is. That doesn't matter. So let's blow this picture up because, well, actually, let's draw the rest of it before I keep going here. One more minute. So this keeps going. The bug then reaches some maximum, right, where you've gone through half of a revolution. Right here, your wheel revolved halfway around. The bug's at the top now. And then the rest of it kind of looks like the same, just doing the other half of it. So the wheel keeps rolling, and we eventually come back down. Like, it should be symmetric, and symmetric as I can draw. So this wheel, right, it's rolling that way. All right, so how do we describe the position of the bug based on how much angle we've rolled through? Well, it's a little bit kind of wonky. I want to draw a bigger picture for you just so you can kind of see it. Yeah. So let's see what we've got here. So I'm actually going to draw it slightly differently just to make it a little bit easier. Let's say we've done this and we've gotten to that point there. We're going to keep going through. Yeah. Let's say the center of our circle is right there. And we're going to look at this angle theta here. Let's label a few things. So let's zoom in. Cool. Wow, I can really see it. Great. So we want to actually figure out what that point is right there. So that's x comma y. And we have a few things. We can say, well, if we drop a perpendicular here, there's x, there's y. This length here is r times sine of theta. I guess I should say what r is the radius of the circle. Apologies. R right there. So that's r sine theta. And this part here, which I've just kind of made it hard to label, That part there is r cosine theta. So if I want to then think about how much my x and y are, well, x is going to equal, it's actually kind of weird. So x is the r times the inverse cosine of 1 minus y over r. That seems very not intuitive, in my opinion. Yeah. Yeah, I don't love that at all. Oh, that's because it's not all of it. It's really complex. Sorry, there's even more. I apologize. Minus the square root of y times 2r minus y. That seems terrible. Nobody likes that. Fortunately, we don't need it, because what we're going to do is we're going to write this in terms of a vector valued function. So instead of describing it this way, what we're going to say is, well, if I'm over here, I can say that my position based on the angle I've rotated through is going to be, well, the x coordinate, this whole length here is r times theta, which might be kind of hard to think about, but think about it this way. The circle, right, you really rolled out this length of the circle, and that arc length is exactly the radius times the angle you've rolled through. So that length is r theta, but then we want to, and which maybe I could label. And then we're going to subtract off this part here, which is r sine theta. That's the x coordinate. And then the y coordinate, well, we are this high. So we're the total height r minus this little part here, which is r cosine theta. So if you roll through an angle of theta, you end up at an x coordinate of r times theta minus r sine theta, and a y coordinate of r minus r sine theta. Or to make this a little bit easier, what people typically do is we let the radius equal 1, and we replace theta with t to say that the position after an angle of t is going to be 1 times t minus 1 times sine of t, comma 1 minus 1 times cosine of t. So that's our position function as a function of time. So just to kind of go back here, just to make it make sense to me, or to make sense to you, make sense to everybody. If I look back here, right, this point here would have been when time equals pi, because that's halfway through the rotation. If we plug in pi, r of pi should be, well, let's see, it's be pi minus sine of pi, comma 1 minus cosine of pi. Pi minus sine of pi, well, that's pi minus 0. And 1 minus cosine of pi is 1 minus minus 1, which is 2. And that makes sense, right? If we go through halfway of the length, right, you're actually literally going a length of pi, x coordinates pi, and if the radius of the circle is 1, then you're going to be at a height of 1 plus 1, which is 2. So it seems reasonable that that's where we're ending up at. Okay. What's interesting, I think, about this kind of vector valued function is that it really is describing any point on the cycloid with a vector. And this is something that maybe wasn't always 100% clear to me when I was a student. But if we draw this again, even though it's not the thing I'm best drawing. So here's the cycloid again, looking like this. And it does have a very sharp corner here, or I should really say a cusp. I can describe any position by the vector, like that position right there is the vector r of pi. I'm getting the point pi comma 2. Or for example, if I do r of 2 pi, well, I suppose I could write my function again. R of t equal to t minus sine t. I'm a 1 minus cosine t. R of 2 pi is going to be 2 pi comma, I should say 2 pi minus sine of 2 pi, which is 0. And then 1 minus cosine of 2 pi is 1 minus 1. So I get 2 pi comma 0. So r of 2 pi really is that vector there. And it ends at the point that is on the curve. So we have all these kind of position vectors that just tell you the point on the curve. What time we got? Oh, we don't have very much time. Yeah, not a lot of time left. I will just say, because it's interesting, the velocity of the bug, just r prime of t, is going to be 1 minus cosine of t, comma, sine of t, which is definitely not constant, right? The velocity at time 0 is going to be 1 minus 1, comma, sine of 1 minus, yeah. Velocity at time 0 is 0? Yes, so. How boring. Did I do my math right? 1 minus cosine, yeah, that's right, yeah. So I guess if we're, yeah, interesting. Really interesting. Is that also true at 2 pi? I mean, it should be, I think. Let's check. The velocity at 2 pi should be, the vector is going to be 1 minus, I mean, right, it's the same thing. 1 minus cosine of 2 pi is 0. Sine of 2 pi is 0. Right. What I think is happening is like you're going really fast, but then you're essentially going, you're kind of going, right, the bug's going downwards, but then when you change directions, right, your velocity had to, if the function was continuous, go through 0. So you've gone from essentially kind of a one direction to a different direction. So yeah, I guess that makes some sense. Whereas, interesting. Yeah, totally. Yep. And then the velocity, say like pi, would be 1 minus cosine of pi, which is 2, and sine of pi, which is 0. The velocity right up here, not surprisingly, is going in that direction. See you, Madison. And the magnitude of it, just because it's interesting, would be 2. So the speed there is also 2. That's kind of neat. Velocity definitely is not constant. So we wouldn't expect the acceleration to be perpendicular to the velocity. All right, I should stop talking. Yeah. Cycloids are kind of neat.